First you. Okay, so we have the definition which we gave last time for the congruence relation. So very quickly, just to review, A congruent to B modulo n. So we say A is congruent to B. Well, I wrote this out last time, so A is congruent to B modulo n. Written as above, to mean that n divides the integer a minus b. And if a and b are both divided by n, to leave remainders, remainders R1 and R2, where 0 is less than or equal to R1 and R2, they're both strictly less than n, then A congruent to B mod n is equivalent to R1 being equal to R2. Okay, that was the connection between congruence and the group and the remainders left upon division. Okay.
Of course, you do need to have this condition that you're talking about the smallest non-negative remainders.
Yeah. That's why that's really what we mean when we do integer division. Yeah. Okay. So we discussed that last time. So let me go into part B, which is one of the key properties. So there are several key properties of the congruence relation, and how they relate, how they mesh well with the operations of addition, multiplication of integers. Okay. Basically, the operations of addition and multiplication can be extended consistently to give you operations on the congruence classes. You add two congruence classes by picking entries from each one and adding those together and look at the congruence class where you land up. But because that relies on making a selection of a representative out of the two congruence classes, you want to know that it doesn't matter which representative you pick. So it's a well-defined operation. So you'll always end up with a sum or a product in the same congruence class. Okay? So you can uniquely define what the sum of two congruence classes is by picking any representatives from either one, adding them as normal integers, looking at the congruence class of that integer, modulo n, and that's the sum of the original two congruence classes. You don't get different answers. You get different integer answers if you pick different choice of representative, but not a different congruence class in the sum. Equally for products, and this is what you're asked to prove here is that property for products. Okay, so we let A be congruent to A prime, B be congruent to B prime modulo n. And we want to show that A times B is congruent to A prime B. Okay. And we'll be doing it using the definition, okay, that we just introduced in part A. So this was a standard result that we proved, but you might be in the exam, maybe you don't immediately, you probably haven't learned it off by heart or anything. So, how should we think about this in kind of reconstructing the proof? Just using some kind of guidelines and sensible ways of thinking about this. Well, we've just gone to the trouble of quoting the definition. So even before we go any further, we've made these two assumptions about congruences. So, i.e., we could say that n divides, we could unravel these two assumptions. N divides A minus A prime, and n divides B minus B prime, and that's true by definition of congruence. And then we look at where we're trying to get to. We're trying to get to the conclusion, you can put it down here, we're trying to get to the conclusion that AB is congruent to A prime, B prime modulo n. Okay, that's the conclusion, given the question we're trying to get to. And it's all going to turn on the definition of congruence in terms of divisibility. So what divisibility statement do we need to
establish in order to make this conclusion? Well,
you need to reach this divisibility statement, that n divides the difference between AB and A prime B prime. So we need something to imply that. So these are our inputs, these are what we like to use, and we want to conclude this. And along the way as well, we can use any properties of divisibility. Okay?
as long as we carefully state what the properties we're using. So you have to find n as a factor of
Those two. So let's say we manipulate the difference AB minus A prime B prime as follows. So, everything I put down there, just comes from the way the question is asked. I haven't really started puzzling it out yet.
Well, I have, but the first stages of puzzling it out is just to make your start point clear, your end point clear. Try and get a feel for how the argument's going to go. So you turn the congruent statements into divisibility statements, and then you're going to use divisibility properties to link the two of them. You could go one step further and turn the divisibility statements into, unravel the definition of divisibility and get right back to just pure arithmetic with the integers. But we don't have to drill that far down. We can instead appeal to properties of divisibility to show this.
So, okay, I want to discover n as a factor of this, and then I know n is a factor of these differences. So I want to take these differences and use them to construct this difference. So I haven't got it learned off by heart or anything, but I know that
it basically comes from trying to construct this as the product of these two. Of course, this equation isn't true yet. We try and do this. There's some corrections needed. We do indeed get the product AB. We do indeed get the product A prime B prime, but it's got the wrong sign. It's got a plus sign over here. It needs to have a minus sign. And we also have these cross multiple terms, A minus B prime, minus A prime B, which aren't present here. So we have to correct for all of that.
Okay, so we get plus A prime B prime here, but we want minus A prime B prime. So we have to subtract 2 A prime B prime. And then these cross multiple terms, you have to get rid of those. So you've got minus A prime B, so you want to add on A prime B, and you've got minus B prime A. So you want to add it on. Okay. Now that equation is correct.
Okay. The left-hand side is equal to the right-hand side. If you multiply all that out and cancel it down, it comes to the left-hand side exactly. The advantage of writing it this way is you're starting to bring out the dependence on these differences. We know these differences are divisible by n. If we can just kick the rest of it around, get it in terms of these differences,
A linear combination of those differences, then we'll be able to conclude divisibility. So I leave these two I'm happy with, because I know this product is divisible by n, divisible by n squared, in fact. So what have we got here? Well, we take these minus 2 copies of A prime B prime and pair one with this and the other with this, and then you get your differences again. So when you pair it with this B here, I can take minus A prime B prime and this plus A prime B. So I've got an A prime into B minus B prime. So that term, A prime into B minus B prime, that accounts for this here and one of these two. Minus B prime, A prime, one of those two. The other remaining negative one, I partner with this, and I take out the multiple of B prime this time. And you've got B prime into A minus A prime.
Okay, so that's the thing I need. Now, if you had that memorized or something, I guess you could legitimately say, just go straight from this to this, just make a comment, when you expand that right-hand side, everything cancels down to the original left-hand side. Okay. But now, what we're seeing here is these quantities here, we know to be divisible by n. Okay? So we've just got a linear combination of things that are all divisible by n, and we can then appeal to that result about the divisibility of the linear combinations. Okay? So therefore, I can say n divides ab minus a prime b prime as ab minus a prime b prime is a linear combination of a minus a prime, b minus b prime, both of which are divisible by n. Okay, so I've carefully stated that property that I'm using, divisibility of the linear combinations. And these are known to be divisible by n up there. Okay. And that's done the job of linking up, filling the gap in the argument, okay? Because we concluded n divides this difference, so therefore these two things are congruent, and that's again by the definition of congruence. Okay, so every significant step is justified. I'm manipulating here, just doing some symbolic algebra here. Here I'm appealing to the divisibility of linear combinations, and here I'm referencing the definition of congruence relation. Okay. So something like that, I think, ticks all the requirements, and we'll get full marks. Okay. But notice the key steps are justified using the definition and the result about the divisibility that we're relying on. Okay. Okay. Any questions? Yeah.
I think it's more concise if you avoid divisibility.
If you go straight to unravel it down to the integer level.
Yeah.
Yeah, okay, for sure.
Like a lot less steps.
A lot less steps, yeah. So you've written a minus a prime as something times n?
A
Yeah.
equals kn plus b, c equals jn plus d, and then just multiply them. And then you can just take a factor of n out.
Okay, yeah. So you've written a as a multiple of n plus a prime, have you?
Well, you've labeled it differently. You've done
Yeah.
A congruent, B, C congruent. Yeah.
But then you just get this.
Yeah, for
Take
sure.
n out and then just
Okay, yeah. So somewhat, if you unravel, so what you've done is you've kind of gone straight from the congruence relation and unraveled it to just a statement in integers.
Yeah.
And then multiply them together, you get a polynomial, some kind of linear combination term where you can pick out terms that are divisible by n, and the remainder term is the a prime b
you don't have
prime.
to add or remove any terms.
I like this way because it's kind of making use of some of the theory we've already put in place. But yeah, there are often,
Would you get marked down?
unless it's specifically said by exploiting properties of divisibility or something. But if it just as the way that question is written now, that approach.
So if any questions say prove something, you can do whatever proof you want, as long as it's
Well,
not
then, yeah.
like we talked about, as long as it's not circular.
Yeah, it should be circular, and it should be in keeping with the spirit of the question, in that way.
So what, using theory, we have done.
Yeah. I'm not doing a shortcut. I was discussing this with the group theory students the other day, like,
Not using results that we haven't.
yeah, not just saying, oh, this is just not like you're asked to prove something, and not just saying, oh, it's true because there's a result in the course, which is that result. Or something,
Yeah.
Yeah.
But as long as we use theory, we have to.
Yeah.
Okay.
Okay. Just make sure you put in a justification. So you're kind of using the equal remainders kind of idea for the definition of incongruent, because you're going from the statement, well, kind of, yeah. No, it's any other questions? So when you're faced with these kind of problems in an exam, it's not necessary to have learned them off by heart or anything. I think you can sensibly, reconstruct these arguments just with, remembering the key idea from each thing.
And then these guidelines are clearly setting out your assumptions. Clearly, it's almost always possible to get down the conclusion you're trying to get to and maybe walk the conclusion backwards a little bit. And then you leave yourself with a gap which has to be puzzled out or filled in.
Yeah. Okay. So part C and D are back to maybe some more calculation type stuff using results in the course. So in part C, we've got a linear congruence. And you're asked to use results about solutions of linear congruences to find all the solutions of this. And that result is printed in the exam handout. So as long as you understand it and you know how to use it, this should be quite straightforward. And then in part D, we're given an additional linear congruence, which is kind of just the declaration of a congruence class mod 59. And you're asked to find all the solutions of the congruence in part C, which also satisfy this. Okay, so you're looking for simultaneous solutions of those two. But again, as long as you're familiar with the Chinese remainder theorem, you'll have the precise statement of it there. So it should just be a matter of, executing it, gaining the marks, okay? Okay, so let's do this. So 3 part C. So, yeah. So we consider 18x congruent to 13 mod 44. So the first step here is to examine the greatest common divisor of the x coefficient with the modulus. Okay? So firstly, GCD of 18 and 44, and that's 2 by 9, so it's just going to be 2, isn't it? GCD is 2. And 2 does divide 30, the constant coefficient. Okay. So there are solutions. So there are solutions to this. So that's by the result on linear congruences. And there are 2 solutions. Start. And these are given by x congruent to t and x congruent to t plus, that's going to be t plus the new modulus. So the new modulus, when we reduce this modulus down to 1 congruent to 22, we'll find one unique solution to that, and then we look at another representative of it. So we're going to look at t plus 22, divided as 44 over 2, just to emphasize where it's coming from, t plus 44 over 2, where t, so these will be the solutions modulo 44, 2 solutions to the original congruence. Where, now what's this t? T is the unique solution modulo 22 to the reduced congruence, which is going to be 9x congruent to 15 modulo 22. So The original congruence is divided all the way across by the greatest common divisor
to get this new one. And
what's the solution of this going to be? Well, to get the solution of this, and yeah, so this will be equivalent to x is congruent to 9 inverse times 15 modulo 22. Okay. Or 9 inverse. I mean, you maybe don't have to write, maybe this is clear from the context, but this is the multiplicative inverse of 9 modulo 22. So we should declare what this is. Now this we might be able to just spot this in our minds, or we might have to do a little side calculation to work out what the inverse is. So we're looking for something that when you multiply it by 9, you get 1 modulo 22. 5, so 5 times 9 is 45. Yeah, which is 1.44. Okay, so it's just some quick trial and error can get it to us. Okay. So 9 inverse is congruent to 5 modulo 22, as 5 by 9 equals 45, which is congruent to 1 modulo 22. Okay. So T is the solution. T congruent to 5 by 15, which is 75. But modulo 22, so 3 is 66, so 66 plus 9, so it's 9 modulo 22. That's the standard representative of it.
so now we've got our one solution, our unique solution mod 22 to the reduced congruence, and this solution then is going to generate 2 solutions to the original problem, and the 9 and the 9 plus 22.
So we obtain 2 solutions to start as x congruent to 9 and 9 plus 22 modulo 44. These are 9 and 34.
There's no point going to another representative of the solution to the reduced one, because if you add 22 again, you're going to get 9 plus 44. 9 plus 44, which is obviously congruent to 9 modulo 44. So you just get back to this solution. Okay. So every representative of the solution to the reduced congruence is congruent to one of these. Yeah.
So those are two distinct solutions to the original problem. Okay.
Are we allowed to just state the multiplicative inverse if we find it, or do we need to use like either tertiary function to try and figure it out?
Yeah, so if the numbers are easy and you realize what it is, yeah, you can use it. But just it's no harm, at least in one position, to just indicate that you understand what the the inverse is.
How you got to it.
Yeah, no. So I wouldn't. That would be fine. Yeah.
Okay, but if you can't, don't panic if you can't realize what it is in the exam, or if the numbers are big,
Then we always have the option of you can run the Euclidean algorithm between
run the Euclidean algorithm between 9 and 45,
and get a linear combination of 9 and 45 equal to 1. And whatever the coefficient on the 9 is, that will be the multiplicative inverse modulo 45.
modulo 22.
Sorry, you run the Euclidean algorithm between 9 and 22. So we're looking for the multiplicative inverse of 9 modulo 22.
Okay then.
Can we just give our answers as like square brackets? Because it says like congruent class. Or is it alright?
You can if you want, but that's declaring congruence classes as well, because the solution is x congruent to 9 or x congruent to 31. Yeah. That's okay, but you can
Just
like,
wondering if you wanted more or something like that.
I think that's equivalent, that's
Okay.
formula now. Yeah. Okay. So use the Chinese remainder theorem to describe all the solutions of the congruence in part C, which also satisfy it's congruent to 5 modulo 59. Okay. So this is a good question. Okay, so we've got x congruent to 5 modulo 59. And we've got x congruent to, now how should we go with the original? Yeah, so the original congruence is 18x is congruent to 30 modulo 44. But we now know that this system of congruences is equivalent to x congruent to 5 modulo 59, and then x congruent to 9 modulo 9 or 31 modulo 44. Okay, so that's the solution we found from part C. So this is going to give us two solutions. So there will exist two congruence classes modulo the product of those two. That will give us the solutions. So by the Chinese remainder theorem, there are two congruence classes modulo 59 by 44 that solve this system. Okay, so we need to gather some ingredients. We need to gather some ingredients together in order to do this. First of all, ingredients for the CRT is we have this number capital M, which is the product of 59 by 44. Which go for calculator here, number 44. 2596. Oh, first of all, we should put in somewhere the CRT applies since GCD of 59 and 44 is equal to 1. Okay. These are co-prime. 59 is prime itself, and 44 is 4 times 11, 2 squared times 11. Okay, so yeah, and then we have the number M1, which is going to be this product M divided by little modulus little M1, so it's going to be 44, and then 2 is going to be the other one, 59, and then we also need their inverses. So M1 prime is going to be the multiplicative inverse of M1 modulo its modulus, modulo 59. This is going to be the inverse of 44 modulo 59. Okay, we're going to struggle to get that one just off the top of our head.
44 is also, just in case there's a clever way, 44 is, you can think of 44 as,
Minus 15.
yeah, minus 15, but that doesn't really help you much. It's not really particularly easier to get the inverse for minus 15.
If it's minus 15, would it be?
Oh, you're right.
Minus
Okay,
4.
so it is easy, yeah, because we're talking 60. Yeah, 15. Yeah, good.
Good spot. So this is congruent to the multiplicative inverse for minus 15 modulo 59, which is the same as the negative of the inverse of 15 in modulo 59. And you're quite right, the inverse of 15 is 4,
Because 4 times 15 is 60, which is one bigger than our 59.
so 55 modulo 59.
Okay, so that's good. M2,
M2 is prime, is going to be the multiplicative inverse of M2 modulo little m1, modulo little m2, modulo 44. So it's going to be the multiplicative inverse of 59 modulo 44. At 59, you can reduce, it reduces to 15. Yeah, 15 modulo 44. And so what's the inverse of 15 modulo 44? Can we spot this one? Huh?
3.
Oh, 3, of course, yeah. 3 times. I'm woeful at this.
you got so much better than me. 3 times 15 is 45. Yeah,
45. 45 is congruent to 1 modulo 44. So it's 3.
So we've got our new modulus, 2596. We've got our 2 kind of divided total modulus, capital M1, capital M2. We've got their inverses. We've got the congruence classes we want to reproduce. So, but now we've got to do it, we've got to do 2 applications of the Chinese remainder theorem. Okay, so we have 2 separate congruence classes, modulo 44, that generate solutions to the second congruence. So one solution I'll label the original system as star star. Star star arises from x being congruent to 5 mod 59 and x being congruent to 9 modulo 44. And this is equivalent to, by the Chinese remainder theorem, x being congruent to, so what we take is we take the congruence class mod 59, which is 5, we multiply it by m1, yeah, which is 44, and then we multiply it by m1 inverse, which is 55. And then we add to it the congruence class mod 44 we want to get, which is 9, multiply it by m2, which is 59, and multiply that by m2 inverse, which is 3. And this is to be interpreted modulo 2596. And you can see how it works, because when you consider, just to double check, this it's a good thing to pause at this stage and just check that it works, which gives you confidence that you've put everything together properly. Because when you look at this at its expanded state like this, before you bring it down to one number, if you consider what this is modulo 59. Well, modulo 59, well, you easily see that this part is 0, so it's got a 59 in it. And 44 and 55 are inverses of each other modulo 59. So they multiply together to give you something congruent to 1 modulo 59. So all you're left with is 5, which is what you wanted, x congruent to 5 modulo 59. And then when you consider it modulo 44, well, modulo 44, there's a factor 44, so this whole term is 0. And the 59 and 3 are inverses of each other modulo 44. So when you're considering this modulo 44, 9 by 59 is congruent to 1. So that leaves you 0 plus 1 times 3. So it leaves you, 0 plus 1 times 9. That leaves you with 9 modulo 44. Okay? So yeah, we confirmed to ourselves that we put them together in the right way. So the justification for that is by the CRT, which I'm assuming. And then you just bring that just to a nice number. 5. Oh, okay. 5 by 44 by 55 plus 9 by 59 by 3, 13,693. $713, is it? What did you get? 713 modulo 2596. I mean, it's nice to get it into standard representative for that Commons class. Okay? So that's just one of the solutions to our system star. The second solution is going to come from taking the second solution, the second Commons class that solves the second. Other solution to star comes from, so you still got your x congruent to 5 mod 59, but now you've got x congruent to 31 modulo 44. And that's equivalent by the CRT to, so you still got 5 by 44 by 55 plus, and this time we got 31 by 59. Seems to be 17,587. Six times 2011. So again, the justification there is by the CRT. So you can see how we've done the question. Use the Chinese remainder theorem to find all the solutions of congruence in part C, which is the 18x congruent to 13 mod 44, which also satisfy this. Express your conclusions in terms of congruence classes modulo a suitable modulus. Okay, well that's referring to where in the Chinese remainder theorem, the suitable modulus where these solutions live is modulo 2596. So the kind of final answer is these two solutions. Okay. So we did question 4 we did previously. We started off with question 4. So that's a full run through last year's exam paper. And I'll be seeing you in the tutorials tomorrow. So if there's any remaining questions, any particular
things you'd like me to revise for you. In fact, it'd be good if you did have suggestions like that or requests for things to look at. It'd be a good idea to send me a quick email today, just so, and then I can put something together for that, or what you want. So if any particular requests for the tutorials tomorrow, just email them to me. Otherwise, we can have a look at some other past papers and some other example problems. Okay? And we're almost there with the courseworks, myself and John. We're nearly there. Get the results as soon as we can.
Does it get online? The results.
Oh yeah. I'll
I don't have to come in. So
no, I'll communicate the results to you and
Alright.
scan.
Well,
We go through, when we convert to from Cartesian to polar coordinates,